Today we are going to learn how to find volume by shells. Let's say we wanted to find the volume of the solid generated by, let's make this x squared plus 1 and a vertical line, let's say at x equals 2, and we're going to generate our solid by going around the y-axis. So our region is this area in here, and we can calculate the volume using washers and discs, but it's not the most convenient because we'd have to set up two different integrals because we have two different types of rectangles. So the alternative, right, same region around the y-axis, is to set up rectangles that are parallel to the axis of revolution. Now, if you can imagine kind of wrapping this rectangle around our y-axis here, this single rectangle is going to give us kind of a hollowed out cylinder. And we want infinitely many of those. And when we add up their volumes together, we would get the volume of the entire region. Okay, so one more time I'll draw the region. We're calling this x squared plus 1. And x equals 2 around the y-axis, but if we use shells, we draw our rectangles so that they are parallel to the y-axis. And the way shells work is our coefficient is 2 pi instead of pi. We go from 0 to 2 on the x-axis, 0 to 2. And then we find an expression for the height of the rectangle, and we multiply that by the distance between the axis of revolution and the rectangle. And because our rectangles are vertical, we're differentiating with respect to x. So that's 2 pi, 0 to 2. The height of the rectangle is top minus bottom, so we've got x squared plus 1 minus 0. I'm not going to write the 0. And then the distance between the axis of revolution and the rectangle here is some x value. So this is x plus 1 times x dx. So you can integrate by hand or use your calculator, and this should come out to be a volume of 12 pi. You should get the same exact volume if you decided to use washers and discs instead here. It's just here it's a little more convenient because we only have one integral instead of two. Okay, one more note about shells. Let's, same region, and instead of going around the y-axis, let's go around x equals 3. So we're taking this same region in here and we're wrapping around x equals 3 instead of the y-axis. Now again, we can use discs and washers, but we would need two integrals because we still have two different types of rectangles and we'd be differentiating with respect to y. Now if I draw my rectangle vertically, it will be parallel to the axis of revolution, so I'm looking at shells. The coefficient is 2 pi. We're still going from 0 to 2, and the height of that rectangle is still x squared plus 1. But the distance from the rectangle to the axis of revolution is a little bit different. That's the distance from here to here. Now we know that this distance is some x value, right, from the axis, the y-axis to the rectangle. And we know that the entire distance from the y-axis to the axis of revolution is 3 units. So we know that this whole thing is 3, that this little part is x, which means that the distance from the rectangle to the axis of revolution must be 3 minus x. And our rule of right minus left still works. It's still 3 minus some x value, right minus left. So 3 minus x dx. And you can integrate by hand or using a calculator. You'll get a volume of 16 pi.